Is that working? Awesome, works. All right, thank you for coming today. It's Fengyuan and let's presenting our work. Let's see a video first. So this is a very simple thing in the VR. So basically 3 components: the tracked hand, the tracked phone, and the touch data there. And it's very simple that just people continuing touching on the phone there. And let's see what's going on. So long-term shot, the wireframe represents the raw data from the Oculus, and you will see that just during the touch, there is a significant errors between the touching point. But with our algorithm, we just anti that drift and calibrate it dynamically to make sure every time once your virtual hand touching on the phone, it will at least looks like it's located on the correct position. Okay, so that's the case. So using the phone and the VR AR together is trending recently, and lots of research work has done in this area. But once we're trying to do those amazing work in VR, there is a specific issue called an ineffable tracking errors when touching happened. So that is because the current state of the art for the tracking stuff, it is the accuracy cannot actually reach into the touching requirement, not only visually, but also for a perceptual to making the visual and haptic coincidentally. So, and different from desktop, there is a specific issue called the Z-depth issue, so which means once your touching happens there, potentially your virtual finger will penetrate the screen, or even you feel your finger is still floating there, like called floating on touch. Such thing is actually severe and actually will creating a coincidence for the haptics and the visual. And it's difficult to fix because for most of the commercial VR headsets, once you're looking into the phone, the camera plane is actually perpendicular to where your finger typically going there, right? So which means that it's difficult to solve in the traditional CV method. And meanwhile, it's actually another long-term issue that the phone itself is reflective. But which means that if you're using CV-based algorithm, regardless you're using mark or key point, it will have some random noise because your shadow also looks like a hand. And the existing work actually trying to using some other method called video segmentations, either like just for using the 2D or the point cloud. They're working pretty well, frankly speaking. But the problem is if you try and want to switch in between the current commercial stuff, like you have a 3D model, you want to transfer from there to such a stuff, it will always be an issue. So our approach, so we actually solving this problem by 2 approaches there. So one way is actually we revert it back. The issue here is we tracking 2 components, one's your phone, one's your hand. Why not we just delete your hand there? And similar to how you're actually using the controller in the VR, we just render the phone. Potentially everything works, right? But actually, once we're trying to doing the literature review, no research like that works. That's why we're doing a study to evaluate whether people can barely on the perception to make things work. Regardless whether that thing works or not, of course, using a hand will be ideal, right? So we actually getting a dynamic calibration algorithm, which combines the touch data and the tracking data all together, and we evaluate it and find it works pretty good. Okay, so let's go. The perception. So basically, you will say that that is something people will say, actually, we render more. So you don't say you're touching on the phone there. In the VR, you actually don't say it. Actually, it works good. The study here, actually, we evaluate 3 different postures here. Because like the body relative frame will actually potentially influence how the performance here, right? So think of it, if you're holding the phone or not, of course, you feel it's different. And we designed such a 3 steps to determine a different level of the body relative frame. And meanwhile, we're doing a user study based on a very traditional touch for the phone study, which is on-screen and off-screen with a different combination of size and distance. Please save our paper later for more detail. Results actually astonishing for us at the beginning that the overall data looks reasonable. So the touch error is less than 8 millimeters for most of conditions, including the off-screen task for the mounted condition, which means that your phone is floating on air, which is actually we don't care too much. So which means that if you are a designer just trying to making something work, like using the phone in the VR, you can decide just not to render the hand, it actually works. Specifically for the posture there, so for the on-screen condition, like the posture has no significance from our study. But meanwhile, for the off-screen, that means that you're moving your hand at the beginning to touch on the phone. That matters. Very tradition. Size and distance works exactly as how Fitzgerald works with tradition and expected. After that, we introduce our dynamic calibration algorithm. So the idea there is super simple. So imagine in VR, everything is properly work. Every tracking is ideal. So once the touching happens, the touching point spatially should be exactly at the point with your virtual fingertip, right? If that thing happens, it means your tracking system work. But frankly speaking, that won't work because the tracking error is there. So maybe the best option there is we calculate that delta and then just eliminate it by some calibration method. So this is just talking about the detailed stuff, like how we actually get it. Long-term shot is once the touching happen, you're getting the 2D data there, calculate where it happened in the 3D, and then calculate the delta here and apply a proper weighted offset method, which we cannot include in such a slides. Please our paper for later. That is simple, right? But once we're trying to deploy, we're actually finding an issue which is called the fingertip estimation. So if you are doing VR and familiar with the development, you will suddenly realize that we cannot directly using the collision detection specifically works in VR at the same time. Because once the touch happens, your finger potentially already, virtual finger already penetrated or potentially floating there. So there's no intersection in the game engine. And it's very expensive if you literally just do a mesh-based intersection real time. And the previous work, specifically doing something like the measurement, always will estimation that the fixed fingertip will be used here. For example, if you're using a Vicon holding there, you will pretend the point will always be here. It works for study, but in practice, it have different postures and better not to do so. So our solution here is that we're using a conceptual paper which was done in 2011, talking about how actually the touch happened, how the people touching on it. So in this paper, and we just deployed it in the VR, long-term shot is we just render interesting point inside the virtual finger, and using that interesting point, shooting a ray perpendicular to the screen, and such that we will get an estimated point that the user tending to touching on. And if we then link this line together, the intersection between the virtual mesh should be the estimated fingertip. Of course, it's not 100% accurate, but it's compared to the fixed point, should be working way better and also working proper. In our very early stage of the art, we tried the gaze, but that's not working so properly. So here we're using perpetual model. For more detail, also refer to our paper. This tool is just basically copy paste from our paper to show how the process goes here. This part for the dynamic calibration process is something we trying to avoid the penetration issue. That's why we need to calculate the velocity here. Okay, to evaluate, of course, we're doing a user study. Here's the major condition here. Of course, one thing is apply or not apply our algorithm. Cross whether your hand is opaque or transparent, because what we're using for the interesting point actually matters whether your hand is transparent or opaque. We want to know whether that's an influence or not. Minor condition, different distance and size combination for sure, easy. And we measure stuff. So the arrow here, different from the traditional study, what we measure is the z-depth arrow, which is just we calculate about whether your finger penetration or not, or floating there. Virtual arrow distance is the total spatial Euclidean distance. Physical arrow is raw data we're directly reading from the phone. And to better evaluate whether our estimation works, we're adding a projected arrow distance here. Results. Overall, so this part is applied and this is not applied. Just from your naked eye, you will find that our algorithm works, right? This means that just for z-depth, virtual arrow and physical arrow, they are reduced somehow. And specifically for the projection distance, there's no difference between applied and not applied, which means that our estimation algorithm works and won't actually influence the results. And no significance is related to the visual representation of the hands and no significance over time. Why that thing matters, especially for the visual representation, potentially we need to measure more. Okay, discussion and future direction. There are actually, we have more discussions there, but due to a time limitation, I will make it easier. One thing actually important is called the visual jumping issue. So recall what we did is basically we drag your hand once the touch happens, right? Drag it to the correct position accumulatively. Of course, it's not just a one time and we're using the historical data, but even still that 10 out of our participants reported that they have feeling a sudden jump regardless in different conditions. So potentially a transition method should be applied in the future study. And for study for simplicity, we're making only one finger there. Multiple finger, of course, needed for the future. Another thing is more conceptual and widely. So long-term shot, what we do is we holding the phone and doing the touch, right? But the touch can not only happen for the phone, but also for things like tablets or even something like the keyboard in the day, right? And those z-depth errors happens for any kind of surface with interaction for your hand. So using such an algorithm potentially will also help for similar stuff. Okay, that's it. Thank you so much. Any question?